Today we're going to do a chi-squared goodness of fit test. We're going to use this problem from the homework. A hotel offers their guests a chance to spin a prize wheel at check-in to earn special perks for their stay. The wheel has 18 equal-sized slots, each featuring one of the 4 prizes listed below. A free snack, a 10% discount, late checkout, 1 free night. Complaints have risen from guests that the spinner is rigged, and that certain prizes are won more often than would be expected based on the theoretical probability of landing on one of those spots. The prize won from a random sample of 150 spins are as follows: 75 a free snack, 49 a 10% discount, 23 late checkout, and 3 1 free night. Is there statistical convincing evidence that the spinner is rigged and that the distribution of outcomes is not as it should be? Perform the appropriate inference procedure. So obviously, since this is in our unit on chi-squared, we are doing a chi-squared test. How do we know its goodness of fit? And how do we know it's chi-squared if it's not in the middle of our chapter? Well, we're looking at categorical data. We're talking about prizes and how many are earning those, and we have more than one category. So if we were just looking at comparing the free snack, then we might be able to do a 1 proportion z-test. If we wanted to just compare 2 of them, we could maybe do a 2 proportion z-test. But if we want to compare all 4 at the same time, all 4 categories, we need to do a chi-squared test. So this is our chi-squared goodness of fit. Does our sample fit the model that's given? They're giving you the probabilities that you can calculate that something's going to happen, and did our outcome fit that model, the claimed distribution? So our test is going to be the chi-squared goodness of fit. Okay. And then we have our null hypothesis would be that the distribution of outcomes of the wheel is as it should be. And I'm just repeating the question. And then our alternative is always just that it's not as it should be. It's not true. The distribution of outcomes of the wheel is not as it should be. Okay, we'll set an alpha level 0.05. And we need to do some calculations. There's 18 spots. I have to check my conditions. So the wheel is randomized. And then it says a random sample of 150 spins. So 150 random customers. Okay, so we can generalize. And 150 is less than 10% of all potential customers. So we can sample without replacement. And the last condition is that our expected counts are large count. So let's calculate our expected counts. So for the free snack, it's 8 out of 18. It said there was 18 spots. So 8 divided by 18 is 44%, times 150 customers, because it's an expected count. How many would you expect? And that is 66.67. So I have to calculate the probability of each prize, and then if there's 150 spins, how many of each of those prizes we would expect. And then for the 10% discount, there is 5 out of 18. I'm just going to write the rest of these down. Late checkout is 4 out of 18, and free night is 1 out of 18. And then 5 divided by 18 is 0.277, and then times by 150. And my expected counts don't have to be whole numbers. So 41.67. Then 4 divided by 18 is 0.22 times 150 is 33.33. And then 1 divided by 18 is 0.05 times 150. And I'm not rounding in my calculator. 8.33. Okay. So I have my expected counts. They are all greater than 5. So we can use chi-squared model. Okay, so all our conditions are met. We can use a chi-squared model. Our chi-squared statistic is the observed minus the expected squared divided by the expected, and it's the sum of all of those. So we had 75 snacks observed, so 75 minus the expected of 66.67 squared divided by 66.67 plus 49 10% discounts minus 41.67 squared divided by 41.67 plus dot, dot, dot. So I'm going to write the first two plugged in, and then I'm going to do the last one. 3 minus 8.33 squared divided by 8.33. Okay, so this doesn't help me much when there's only 4, but if there was more, then it kind of shows that I understand my formula, how the numbers are plugged in. My degrees of freedom is 4 categories minus 1. There was 4 prizes. So my degrees of freedom is 3. And then we're going to go and put the data in the calculator. Okay. Okay, so in my list, I'm just going to clear everything out. I have my observed in the list 1, so 75. It was 49, 23, and 3. Okay, so those are all in list 1. And then we're going to go over to list 2, and I'm going to put my expected. So here we go. 66.67, 41.67, 33.33, and 8.33. Okay, now here's the best part. We have a calculator command, so we're going to go stat tests. I always go up for chi-squared because they're at the bottom, and the chi-squared GOF is our goodness of fit, so we hit enter on D. You tell it where your observed are, what list your expected are in, and what your degrees of freedom is. So my degrees of freedom is 3. Let's try 3. And then we hit calculate. And there is my data, which is really blurry, but you get the idea. So then I can just write down my chi-squared is 8.94, and my p-value is 0.03. Okay, so all I really need to do is write down 3 components of my chi-squared calculation, my degrees of freedom, and then I can do the rest in the calculator. But this part here shows whoever's grading it that you understand the chi-squared calculation, and they're not really concerned about you doing it by hand, just that you know how it's set up. And so then we say assuming, okay, I just paused it and typed it up so it would be easier for you guys to read, because I know my handwriting can get a little questionable sometimes. So here's my conclusion. The same p-value that we're used to, assuming HO is true. The distributions of outcomes is as it should be. That was our null hypothesis. There is a 0.03 chance of getting our chi-squared of 8.894 or more extreme purely by chance. Because our p-value of 0.03 is less than our alpha of 0.05, we reject HO, and there is convincing evidence the distribution of outcomes is not as it should be. And then we follow up analysis. Why are we rejecting? The largest component of chi-squared was the free night, because the observed count of 1 was much lower than expected. So this is another one of those cookie cutter statements for our analysis. It's the largest chi-square component is blank. And so you fill in what the largest one was. And then we say because the observed number or counts was blank and it was lower, or we say higher than expected.